sort of get this story along. And it's not finished, but I think we've composed a story about the story, so kind of a meta analysis to some extent. But I'll let him take over from here.
Hi, I'm Marcus Shell, and I am a sub-entry level data analyst. So, the title of my talk might have been picked a little bit prematurely, but I'm trying to stick to it as best I can. And it's something that I believe in. And it's called The Importance of a Definition and Understanding a Problem. And we're just going to look at a couple of examples through the data analysis that I've been doing, and I'm going to try to bring it out as best I can. We're going to start with a little bit of a metaphor, though. Let's see.
Down at the end.
Yeah. Okay. So first, I just want to start with a nice little quote. Problem solving isn't about answers. It's about asking the right questions. Whoa. Oh, yeah. Oh, there we go. Okay. All right. So we'll start now with the definition. So what is problem solving? Well, problem solving is the process or act of finding a solution to a problem. And that's the thing. We talk about data science, we talk about mathematics and biology and all these fields, engineering, but a lot of the times at their core, they're just about problem solving. And that's the thing that I really love, is problem solving. And there's that word there at the end, solution, but as a problem solver, I'm not always as concerned about the solution as the road to get there. The solution is important, that's why we do it, but it's the how that is really fascinating and like what makes up the meat of the process. So anyway, so the process requires asking questions, lots of questions. It's all about questions, and such as like, what is the problem exactly that I'm trying to solve? What's another way to phrase the problem? What does the problem entail? And what do I already know? So we problem solve to find solutions, but we have to ask these questions to get there. Try to keep these current. All right, so consider the following. I want to start with a nice little metaphor. Just real quick though, who's actually taken calculus or calculus 2? That's calculus 2, okay, so I see. Oh good, we actually have some hands, so this is going to be really redundant. So consider the following. We've got we want to consider the volume of the solid generated by revolving this shaded region about the y-axis. That's actually the crayon texture for the MS Paint. So we've got our f of x formula. It's a little small, but we've got our f of x formula here that demonstrates that line, and then we've got x equals 4. So when you set up an integral, you would set 4 as your upper bound. All right, so math students often trip over this kind of problem, and they ask questions like, why do I care? Or when will I ever use this? Unfortunately, what they fail to see is that we don't care about the volume when we're in a Cal 2 class. We care about the means of finding it. We care about that process, the problem-solving process. All right, so just real quick, here's how we're going to break this down. We have a quick mental image. We've got this idea of that shape revolved around. It's like a cylinder, but there's like a cone pulled out of the top of it. We're going to say, how would we go about finding this volume? Well, we can use something called the shell method. The way the shell method works is we take our cylinder and we slice it up into a bunch of concentric rings and take them apart one by one. And we take just one of these and we make a nice little cut in it and we uncurl it, and when we're done uncurling it, it roughly resembles a rectangular prism. So we use this formula, this will come up in the textbook, like the volume is the sum of a bunch of other volumes, the volumes of these shells. So they're smaller volumes, and the integral symbol looks scary sometimes when we're not familiar with it, but it's really just a sum, but it's for n, we're taking the limit as n approaches infinity, so we're getting lots and lots and lots and lots of pieces, and eventually we get a really good approximation for what we want. Okay. So the volume of a rectangular prism is what we're adding up. Like we said, we took those shells and we uncurled them, and then we have rectangular prisms, also known as a parallelepiped. Nice little trivia there. And so you probably know, even if you haven't taken calculus, that the volume of a rectangular prism is the length times the height times the width. So in data science, sometimes we're going to have this kind of setup where we have a formula, and I don't really care so much about what comes after that all the time. What I care about is filling in this formula. I have to identify what my pieces are. So in this case, we break this down, we get our shape, and so we're going to identify the height, the length, and the width, and plug that into my formula. So the first question we're going to ask is, what is the height exactly? I'm looking up and down on this, and I'll look back at this ring, okay, and I trace it all the way back to my original shape, and my height on that graph, you remember that sloping line like that? For each individual rectangle I'm looking at, it represents a certain point on that diagonal line. So I can determine what this height is by plugging in the corresponding x value. So for whichever one of the shells I'm on, whatever that number is, I just plug that into my formula, and I get that. So that's my f of x. And then for my length, I'm just going to plug in that same x value, because it's just how far along down the line I got, essentially. Well, actually, I take that back. That's not quite right. So this length is actually the circumference of the circle. So I would plug that in for my radius. So I would have 2 pi times my radius, which is just my x value. And then the width, since we're taking the limit, this is getting arbitrarily small, it's literally just the change in that x value for each one of the prisms. So we're just going to call that change in x, or delta x. And so after all of that, we get down to this formula here, right? And now this formula, this little symbol right here, if you're doing calculus, we're not going to do calculus today, but this is already doing the work. Once you know how to do this, you just plug this in and you calculate it. I mean, if you want to, you can just type it into Wolfram Alpha, and it'll give you a number. I don't care about the number, though. I care about the process of identifying these pieces, because that's my job. The rest is calculus. We've heard the rest is algebra or arithmetic, but the rest is calculus. So anyway, so now we're on to the actual data science a little bit. So the first question I want to ask, like I said, we're all about asking questions. First question we're going to ask, and this isn't actually my question, it's the question she asked, is what happens when you put a bird in a box? Like, just to dumb it down a lot, if you were here for her talk. So here's just a quick rundown. I don't know how much she got into. So we've got the Skinner box, which is named after a person in psychology by the name of Skinner. And basically we put the bird, the pigeon, inside the box, and we run some lights and patterns, and the bird responds. And from there, that box is sending outputs to a computer. And that computer is taking it and recording every single event that goes on, not just what it's doing to the box, but what the bird is doing inside the box. And it puts that into binary. And from this binary, we go through a process of converting it. We translate it from ones and zeros into meaningful values. Call it a table of events, or a TOE if you like. It's also CSV. And then where I came into this, Ted Chandler was a student here before, and he had actually done this step of it here. So my job was to take it from here and actually make some meaningful tables out of it. So I took it and broke it down and organized it, so to speak, and took it from this and made it into tables. But what is this, though? So this is what we call comma-separated values, and every single line on this is a single event that happened in one session, and that's not the whole thing. That thing would be like down there somewhere. And every single event is very literal. It would be nice if, like, just a quick word on markers in a moment, but it would be nice if those were very, very precise. And while they are, sometimes we have to infer from other ones that are kind of related, but they're a 3-digit code. So like a marker is something that serves to identify, predict, or characterize. And in our context, each event in the file is represented by a numerical code. So we've got like a 218 and then 12006. The first digit is an action, and the second digit refers to a specific object, and the last is like a timestamp, or in some cases like a value for an error code. All right, so like from there, well, real quick, okay, so my comment about markers. If you're ever setting up an experiment like this, where you're going to have to do a lot of data analysis and you're going to have to use markers, I really recommend that from the outset you make a marker for every possible thing you could record. Because in our case, whenever I wanted to say, has reinforcement started, I had to look at other things, like, did the light turn off? But the problem is that light may have turned off other places unrelated in the experiment, so I had to look, has the experiment started? Are we past a certain time? Now has the light turned off? And that doesn't sound like a big deal, but in the computer science, when I go to write the actual algorithm, that's a lot more steps I have to check, and it gets really complicated sometimes when you have to do a lot of that. So it's best to not jump through hoops and just define your terms very precisely from the beginning. All right, so what's next? We ask ourselves some questions. What sort of information do I need to derive? How do I quantify it? And then how do I compute it? And then how do I visualize it? And there's some good answers, some existing answers to some of these questions, fortunately. All right, so the process basically, we've already covered, like we collect the data, we translate the data, we format the data, then what? Well, I take the data, and then I run it through some algorithms, and we don't sleep. And then we do some figures and graphs, and we get more data, and then we don't sleep, we run it through more algorithms, and then we get more figures and graphs. Sleep happens eventually, but we can't prove where. So scatter plots are one of the first things we want to do. Like, what do I want to do with my data? Well, one of the first things I want to do is I want to look at the scatter plot. Amanda showed you one of those earlier. We're going to look at one again. But so the basic process for how I program that is I take that list of events and their timestamps, and I say, all right, so I set a counter for the response times and for the reinforcement intervals. I have two axes. How often, like, what's the time between responses, and what's the time in between reinforcement delivery? So each one of those needs its own timer. And then as I go through and I find responses, if I find a response, I record the time that's elapsed and I reset that timer. And I record the time since the last reinforcement delivery, but I don't reset that timer. And then if a reinforcement marker is found, then I record the elapsed time since the reinforcer delivery period ended, and then I skip to the end of the reinforcement period because in our context, I don't want to record what happens there, but I also don't want to account for that time. So I have to make sure that I know exactly when to reset my timers. And this is a very basic version of it. But anyway, so we skip to the end, we reset the corresponding timer, and then if we reach the end of the file or the experiment marker, the end of experiment marker is reached, then we're done, essentially. All right, so that gives us the values for this. It doesn't give us this, but we'll talk more about that at the end if I can get there. So we've got the scatter plot, and every single one of these points, as Amanda said, is a response. But in my eyes, it's not a response. It's an ordered pair. It is an X value that comes from the time since the last reinforcement, and it has a Y value, which is the time since the last response. And we have a few things like this where it's like, that's just like, I guess you could say user error, because the bird like texts and sometimes the button double taps or something. And we can actually filter some of that out a little bit, but that didn't come up quite immediately. So the next question I want to ask is, what is banding? So we see these bands appearing. They're like, I don't know if you've noticed, but there's definitely something going on here. But I need to answer like some questions about it. Now, as far as why it occurs, I'm not worried about. But how to measure it occurring is what I'm concerned with. I've already lost use of these. Just put them in my pocket. All right, so the next step. So question one was, what is my problem? I want to know how many bands there are and how they change over the course of the experiment. And then I'm having to ask, what is a band and how is it defined? So a band occurs when an event occurs frequently enough to create an obvious or a visible pattern. So that's what's happening. The only difference between this guy and this like space in between is a matter of density. It's just density. And you'll notice, like I can say, hey, there's something going on here, but where does it stop? I don't really know. I have to define that. I have to make a decision, or Amanda has to make a decision. We have to make some rule up as to where that begins and where it ends, or maybe we can't, and so we have to define another way to measure when it happens. So how do I measure when a band occurs? That's the problem. There's the rub. All right, so what we want to do with that scatter plot, we've got the banding, and I've got a few of them. I've got one down here, and one down here, and one down here. They're all stacked up. They've all got their different Y values, and I have to determine what I want to do. Like the data we just looked at was practically all of the sessions. What I want to do is I want to look at about 5 or 10 of them at a time and find out where the rough center of one of these bands is and plot that as a point for each one. And then over the course of those sessions, I want to see how is that changing over time. That's not the easiest thing to do, but it's because like there's several factors involved. So this is my hand-drawn version, just so I could demonstrate like why we have trouble finding the center. Like we could say what's a top or a middle or a center or peak, okay. But what we have to do, like if I were to pick a middle, the middle changes depending on how far I am to the left or right sometimes. And the top, like we talked about, is not very clear. So I have to find other means of doing that. So one of the ways we can do that is with a histogram. A histogram, Amanda mentioned earlier, but it basically squashes it counts all the data within a certain bin. I've turned this sideways for the demonstration, so you'll notice the banding's this way. And so what I do is I count the number of peaks within a certain width, and I look at that. And what that tells me is that there's a certain point where it maxes out here and here and here. And I can see that here and here, but with the histogram we start to run into some problems. Number one, this is really noisy. I want to do peak finding, but the computer, if it looked at this, it wouldn't say 1, 2, 3, 4, 5. It would say 1, 2, 3, 4, 5, 6, 7. I don't need that. I need very precise. So then, okay, let's look at this. Except for this is 1, 2, 3. I may have 3 or 4 here. So I need a bit more precision. This is an example of what happens when you use like 4 bins. It's not very helpful. So optimizing that can be tricky, but it's not that it's the wrong answer, it's just that it might not be the best answer, because even when I optimize it, I still have a certain amount of error in it. So that's okay, because sometimes we have to just ask different questions and explore other methods. So some of the things that we are looking at are a sliding average or Savitsky-Golay filtering, and that's just somebody's name, I can't explain. And then current smoothing is something we're going to get into. But we do have examples of the first two. This is Savitsky-Golay filtering, and you'll notice right away that it's really smooth. And this is what I call a sliding average, which is like a histogram, but instead of setting distinct bins, I slide the bin over just a little bit, and a little bit, and a little bit, and I count, and then plot what value it's got at the center of that bin's X value. And the problem you'll see right away is that this is very bumpy. So I still have that same problem with peak finding, is that that's going to give me false positives. And we can kind of get around that. I could widen my bin and get a much smoother curve, but then that curve would be very flat, and I would actually lose some of these peaks. And then with Savitsky-Golay, it does really well, except it requires a lot of parameters, and this is like a lot of tinkering just to get this one right. And even here, that's arguably not a good peak, so there's still a lot of things that would have to be figured out. So we've got some other options to look at, but these are just some of the things we have to look at. Data collection is noisy, it's finite. Math, when you're looking at calculus, you have an infinite sum. We can't do an infinite sum with what we're doing, so we have to do approximation. But after we collect all the terms and define all the things, the variables, and know what they are, and find a way to parse them from the data, the rest is formula. It's all, like, after that, it's just arithmetic. The computer does the rest of that. And as far as the plots, I said I would mention this, just since we're towards the end. All of the graphs, the big graphs we saw, the window and the actual machine that plots those points, I didn't do that part. That's also something that's been done for me by other developers out there that make libraries. So as a data analyst, a lot of that's already done. I just have to give the right information, but that's the hard part, is you have to figure out what is the correct information and how do you automate that. But then the rest, after you figure that out, it's just formula. But thank you.